In this video, we're going to take a look at section 6.2 on rational exponents. So radicals can be rewritten in exponential form, and when you do this, the exponent that gets derived from the radical becomes a fraction. So, for example, if we have the nth root of a to the power of m, and I apologize, this is just the standard way it's done, I think, typically, but m and n do sound pretty similar, so I'll try to enunciate them where you can tell the difference. So we have the nth root of a to the power of m. That radical can be rewritten as an exponent, and I apologize, the formatting here doesn't really capture this as an exponent. I feel like it kind of looks like it's kind of jumbled together, but m over n here is the exponent. So maybe if I wrote it by hand, it would look a little bit better, but it's going to look like this. Right? So having that kind of lifted up in the air emphasizes the fact that it's an exponent. So what I want you to notice is the pattern here, that the root you're taking, which is n in this case, becomes the denominator of your fraction, and the power inside the radical becomes the numerator of the fraction. And then a becomes the base of the exponent where the fraction is going to exist. All right, so for example, we saw in the previous video for section 6.1, we had a problem like this. We had the ninth root of y to the ninth power. Now we simplified this using the concept of an nth root cancels out powers of n. So for example here, the ninth root literally cancels out that power of 9. But you could also think of it this way. You can rewrite this radical as an exponent. The base will be y, and then we're going to take the power inside the radical as the numerator, and then the root that we're taking, which in this case is a ninth root, becomes the denominator. And so this 9 inside the radical gets divided by the root of the radical, which is also 9. So we get 9 divided by 9, which is 1. And y to the first power we can write as just y. And so we can see by this method that the nth root does cancel out that power of n. They divide each other, is what really is happening there. And the exponent becomes a 1. All right. So this is the concept that we're going to be looking at throughout the rest of this video. Let's go ahead and take a look at some examples. So we have 64 to the 1/3 power. What they want us to do with these examples is, if they are in exponential form, to rewrite them as a radical, and if they're in radical form, to rewrite them as an exponent. And for these cases, when we actually have numbers instead of variables, I think they'll want us to simplify if possible. And I think these actually will simplify quite nicely. So a 1/3 power, what we want to do is use this rule we were just looking at in reverse, right? So the rule works in both directions. So if we have an exponential expression where the exponent is a fraction, the numerator of that fraction stays as a power inside the radical. The denominator of that fraction tells us what root the radical is. And then a will be the base of the exponent inside the radical. So what we will get here for this problem, the denominator is a 3, so I usually start with that. That tells me this is going to be a cube root. So whatever the denominator is, that is the root you're taking. That is, that indicates what the root of the radical will be. All right, and so I'm going to put a radical symbol because I'm going to rewrite this exponential expression as a radical. It'll be a cube root, which means I'll put a 3 here to indicate that's a cube root. The 64 will go inside the radical, and we will raise it to the power of whatever the numerator is, which is a 1 in this case. And so we get 64 to the first power, which is just going to be 64. So effectively, what happens here is a 1/3 power is a cube root. So we can convert that power of 1/3 to a cube root in radical form. And we'll take the cube root of 64, and at the end of the video in 6.1, I recommended you memorizing some of these roots. And so for the cube roots, this was one you were supposed to memorize. The cube root of 64, where do we get 64? From taking powers of 3, we get it from the number 4 raised to the 3rd power. So the cube root of 64 is 4. That's a good one just to memorize. All right, we'll do the same thing here. We're going to, in this case, it'll be a fourth root. So the denominator is a 4. So we're going to be taking a fourth root here. And then we're going to be raising this to the third power. All right, let me actually put the right words there. So raised to the third power. All right, now we could follow this example exactly in the same way we did this example. But here's what's going to happen. So we're going to make a radical symbol. It's going to be a fourth root, so we'll put a 4 there to indicate it's a fourth root. The 256 will go inside the radical, and it's going to get raised to whatever the numerator is, so it's going to get raised to the third power. And if you set it up like this, the order that would have to be simplified is the exponent would have to be done first, and then we take the fourth root of the answer, which if you have a calculator, maybe isn't going to be an issue. But this will be a gigantic number. 256 to the third power is going to be huge. And we won't really know, looking at the number, how that should simplify. You would have to use a calculator in that case. It turns out we can actually apply these in the opposite order. So with this, I mean, here's the math behind it. So we have 256 to the 3/4 power. We can write that as 3 times 1/4. Right, we can split the 3 off from the 4 and write them as two separate things. The 3 stays on top in the numerator, so it's just 3. The 4 stays in the denominator, so it becomes 1/4. And then these can be applied in either order, right? We could write it like this. We could write it as 256 to the third power raised to the 1/4 power, which is what we're doing here, right? Where the 1/4 power becomes a fourth root of the 256 to the third power, which again has some issues with the numbers becoming really, really large. We could also apply it in the other order. We could write it as 256 to the 1/4 times 3. All right, whoops. I'm just rewriting the same thing twice. Let me change that. So it'll be this way. So we'll apply the 1/4 power first, and then we'll raise it to the third power. Right. Now doing it this way, what's going to happen is the radical gets applied first. So it'll be a fourth root of 256, right? Because a 1/4 power is a fourth root. That's just a good way to think of these. Like I said over here, a 1/3 power is just a cube root. A 1/4 power is just going to be a fourth root. A 1/2 power is a square root. So if you just know that fact, it makes simplifying these a lot easier. And then we'll raise it to the third power. So in this way, we'll keep the number from blowing up, right? So the fourth root of 256 actually was on the list. It's one that I don't normally think of, as students needing to memorize, but I'm glad I mentioned it in 6.1, so maybe you remember this. The fourth root of 256 is 4. So that simplifies to 4, and then we will raise that to the third power. 4 to the third power is going to be 64. And so that's the answer that we get. So the lesson here that I want to emphasize is that these could be applied in either order. And so you should apply them in the order that'll be most helpful for the situation. And very often, if it's going to simplify nicely, doing the root first is going to be easier. So you apply the fourth root first, then you raise the answer to the third power, which is exactly what we did here. We did the fourth root first, we got 4, and then we raise it to the third power, and that's how we get 64. Keeps the numbers from getting ridiculously big. All right, let's take a look at some other examples here. So this one we want to rewrite without rational exponents, meaning it's in exponential form. Let's rewrite it in radical form. And I already have addressed the way you want to think about this. A 1/7 power is going to be a 7th root. And so I'm going to take the 7th root, which means I'm going to write it as a radical, put a 7 here, that makes it a 7th root, of whatever's in the parentheses, which will be a to the 4th power, b to the 4th power, and that's it. So that's converting it from exponential form to radical form. A 1/7 power becomes a 7th root. So I write it in radical form as a 7th root, and that's all you have to do with that. There's nothing to simplify here. I know it says simplify if possible, but these powers are not big enough to simplify with a 7th root. Because remember, 7th roots cancel out with powers of 7. And so you need at least 7 here for anything to happen. So since that's not big enough, nothing's going to cancel out, nothing reduces, nothing simplifies. All right, let's take a look at another example. So Here we want to rewrite, we're going in the reverse order. It's already in radical form. We want to rewrite it in exponential form. So write this as an exponent. This one's deceptively tricky because it's a very simple radical. It's a square root of 7. We want to write this as an exponent, and the reason it's tricky is because the numbers are invisible. The numbers that we need to make our fraction are invisible. So let's go ahead and make them visible. Let's go ahead and write in what they actually are. So this radical here, because the number is missing, means this is a square root. So the invisible number indicating it's a square root is the number 2, right? So we have a square root here of 7, and because there's no exponent here, it's understood to be raised to the first power. So let's go ahead and write those numbers in. And then to convert this into exponential form, the base will be 7. The power inside the radical goes on top of the fraction. It becomes the numerator. And the root of the radical becomes the denominator. And so we get 7 to the 1/2 power when we convert this to exponential form. And you might also use the thing I mentioned earlier, that a square root is a 1/2 power. A 1/2 power is a square root. A cube root is a 1/3 power. So if you want to use that shortcut here, I can rewrite this as 23. Because this is a cube root, I'm going to raise this to the 1/3 power. And that's all there is to that. Sorry, I don't know why it's not writing here. Okay, there we go. Okay, but you could also, again, fill in the invisible number here, right? So the 3 is not invisible. We can see it's a cube root. But this is 23 to the first power. And to write it in exponential form, this power inside the radical goes in the numerator. The root of the radical goes in the denominator. And so we get 1/3 when we write this as an exponent. All right. Let's take a look at another example. So these are going pretty quickly here. So same thing on this one. Rewrite this as a rational exponent. So not in radical form, but as an exponent. And so what we're going to do with this is a 6th root. So we'll put parentheses here because we have more than one thing inside the radical. So we'll put all of that stuff inside of a set of parentheses. And then because it's a 6th root, that becomes a 1/6 power, right? So just like we talked about a moment ago, a square root is a 1/2 power. A cube root is a 1/3 power. A 6th root is a 1/6 power. And this would be it. That's all you have to do with that one. All right. If you want to see the numbers that we're using to piece that together, again, the root is a 6th root, so that's why that becomes the denominator. So the root becomes the denominator. The power inside the radical becomes the numerator. And because we have multiple things here, what we're doing is grouping it together as one thing raised to the first power. Right? And so the invisible power here is 1 when you put this together as a big group. And so that becomes your numerator. Right? So we have 1 divided by 6. That's how we get this exponent of 1/6. Right? This one, we have a square root here, which means the invisible number, since there's no number written there, the invisible number there is a 2. We're going to take everything that's inside the radical. Because there's more than one thing, we need to put it in parentheses. The root of the radical becomes the denominator, right? It's a square root, which is a 2nd root, which means the denominator will become a 2. And this power here, even though it's outside the radical, you could write this as 1/2, right? A square root is a 1/2 power. But then that power of 5 is going to get copied down, right? We want to raise that square root to the 5th power. So here's the square root. We're raising it to the 5th power. And in this situation, when you have one power raised to another power, you're going to multiply them together. And so you'll get 5mn in parentheses. And when you multiply these fractions together, the 5 goes on top, the 2 goes on the bottom. So it really follows the same rule. Whether that power is inside the radical or outside the radical, that number is going to become the numerator, right? So the root becomes the denominator, and whatever power is there, whether it's inside or outside the radical, that becomes your numerator for your exponent. All right, and so this is how you would write this expression as an exponent. Let's take a look at another example. Okay, so here, this is a different kind of problem. So we're not converting from one form to the other at this point. What we're doing is having exponents that happen to be fractions, and we want to simplify these exponents. And this is something we learned how to do back in chapter 4. We talked about when we add exponents, when we subtract exponents, when we multiply exponents. We talked about what to do with negative exponents, which is the issue with this particular problem. And we have to use all of those rules that we learned in chapter 4 to deal with these problems. So it's kind of a review of rules for exponents that we learned in chapter 4, except now we might have fractions to deal with in addition to positive and negative numbers, right? So what we're going to do with this, we don't want to leave our answer with negative exponents. So remember, the rule for simplifying these kind of expressions is no negative exponents, one of each variable, and then simplify or reduce the numbers if possible. And so we don't want to leave this expression with negative exponents. The way we make them positive is we flip them down to the denominator. So anything that has a negative exponent gets flipped down to the denominator. Anything with a positive exponent can just stay put. And so this x to the 4th power is positive, so we will leave that on top. But this 7 to the negative 2/5 power has to get flipped down to the bottom. When we do, the exponent becomes positive. That's all that we change. So instead of being negative 2/5, it becomes positive 2/5. That's it. You don't have to flip the fraction over or do any other crazy things, right? And when we bring the y down here, this negative exponent becomes positive. So it becomes positive 3/4. And now this meets all the criteria. There's no negative exponents. There's one of each variable. And this number can't be simplified. 7 to the 2/5 power, that's a 5th root of 7 squared, which will be a 5th root of 49. That doesn't even simplify, and so we could just leave it the way it is. All right. Let's take a look at another example. Okay, so we have 6 to the 5/12 power divided by 6 to the 3/12 power. Now I know 3/12 could be reduced to 1/4, but you don't want to reduce it actually, because this is nice having a common denominator here, because what we're going to have to do with these exponents is subtract them. And to subtract fractions, you have to have a common denominator. So again, think back to chapter 4, unit 4. It wasn't really in chapter 4, but in unit 4 when we covered this material, whenever you go to simplify this, the base stays the same. It doesn't cancel out. So if you think, oh, the 6's cancel out, that actually doesn't happen. The base does not change. It'll still be a 6. And then what we do with the exponents is we take the top one, which is 5/12, minus the bottom one, right? So if you're dividing two exponential expressions with the same base, you subtract the exponents, the base stays the same. It doesn't change, right? So we will subtract top power minus bottom power. So we'll have 6. So 5 minus 3 gives me 2. And the denominator, the common denominator, is 12, so it'll stay the same. So we get 6 to the 2/12 power. And now we'll go ahead and reduce that. We'll reduce that fraction. And so we'll get 6 to the 1/6 power. And that'll be my final answer. Oh, I'm doing a really bad job today of writing here. Okay. So here, this is a case where you subtract the exponents. So that's what we did here. And yeah, they're fractions. That's what's going to make this a little bit more difficult to do. Same thing here, right? We have one exponent being raised, or I should say it this way, we have one power being raised to another power. So we learned back in chapter 4 that in this situation we multiply the exponents. So again, the base will stay the same. We have 10. We'll take 7/4 times 2/11. So those exponents get multiplied together. You can reduce first before you multiply fractions. So I'm going to cancel this 2 out with the 4. It'll leave me with a 2 on the bottom, leaves me with a 1 on top, and then we will go ahead and multiply these fractions together. You don't need a common denominator to multiply. So we get 7 times 1, which is 7 on top, 2 times 11, which is 22 on the bottom. And that'll be the final answer. All right, let's take a look at some more examples of this type. So here we're multiplying these together. So in this case, we add the exponents. So again, the base stays the same, right? So the base will still be a. We'll take 2/3, the first exponent, I'll write that 3 again, plus 5/6. We'll add the two exponents together. As I mentioned earlier, to add or subtract fractions, you have to have a common denominator. And this time they were not kind enough to give us fractions that already had a common denominator. So we have to make these denominators the same. The common denominator is going to be 6. So I'm going to change this fraction by multiplying a 2 to the bottom. That'll make that denominator a 6. I'll do the same thing to the top to keep the fraction balanced out. So we're going to get 4/6 plus 5/6. Sorry, I'm thinking of the answer. Whoops, hit the wrong button again. So I will have to just use the eraser this time. Let's see. Okay, I'll just erase the whole fraction and rewrite it. All right, so we're going to get 5. I'm just copying it over, and I can't do that for some reason. Okay, 5/6. Now I can add these fractions together. The denominator will stay the same. It'll still be a 6. We get 4 plus 5, which will be 9. And then, as always, with any fraction, you always want to reduce it before you finish the problem. And so let's reduce this fraction. We can divide a 3 from the top and bottom, so it reduces to 3/2. And that's all you have to do with that. You don't have to convert it back to radical form for this particular problem anyway. So just leave it as an exponent. All right. So for this one, what we're going to do is we'll take the exponent here and apply it to the top and bottom of this fraction. When we do, we're going to have x to the 7/6 power. That's going to get raised to the negative 3/7 power. So when you're taking one power and raising it to another, they're going to multiply together. So we're going to have 7/6 times 3/7 on top for that exponent. On the bottom, we'll have y to the 1/3 power. And again, when I take that power and raise it to another power, those are going to get multiplied together. So we're going to have 1/3 times negative 3/7 as the power for the denominator. All right, and so we're going to get x, the base will stay the same. Here we can reduce before we multiply. A lot of stuff cancels out here. So the 7's cancel out. We can divide out the 3 from the 6. That'll leave me with a 2 on the bottom and a 1 on the top. And so we'll have positive times a negative, which will be negative. And then we'll have, there's just 1's on the top, so 1 times 1 is going to be 1, over 2 times 1 on the bottom, which is going to be 2. All right, so that's what we get for the numerator. For the denominator, we'll still have a base of y. The 3's cancel out, so again, there's 1's left behind when we do that. Then we'll multiply across. We have 1 times 1 on top, which will be 1, and then 1 times 7 on the bottom, which will be 7. And again, it's positive times a negative, which I should have done that first, but as long as I'm catching it at some point, we're okay. So positive times a negative will make that negative. So that's how you simplify the exponents, but we can't leave our answer in this state because it has negative exponents. So that's one of the rules. You can't have answers with negative exponents. So what we need to do is make these positive by flipping them both over. Right? We'll flip the y up to the top. And when we do that, the exponent will become positive. Again, that's the only way it changes when you do this. When you're flipping an exponential expression from the numerator to the denominator or vice versa, the only way it changes that expression is, is the sign of the exponent. So instead of being negative 1/7, it becomes positive 1/7. And on the bottom, we're going to flip the x down to the bottom, and instead of being negative 1/2, it will now be positive 1/2. And this meets all the criteria. There's no negative exponents, one of each variable, and there's no numbers to simplify or reduce, so that's the answer in simplified form. All right. So it looks like we have at least one more here. Let me see, how many more of these do I have? Okay, this will be the last one, and then we're moving on to a different topic. All right, so same idea here, except instead of being a fraction, we are going to distribute this exponent to each factor inside the parentheses. And what's going to happen, just like it did with the fraction, is when we take one power raised to another power, we're going to multiply those exponents together. So we'll have m to the negative 1/4 power times negative 12/7. So those exponents will multiply together, and we'll have to take our time to figure out what that's going to look like in just a second. And the same thing's going to happen with n. We have negative 7/6 here to begin with, and when we raise it to this power, these exponents will multiply together. So we're going to have negative 7/6 times negative 12/7. All right. And then we need to simplify, and I'm sorry, this is in the exponent. I really kind of got bad about how I wrote this, and now it kind of seems like it's back down on the ground level, but this is an exponent here, so keep that in mind. So we're going to multiply these fractions together. Again, we can cancel out first. And so this 4 will cancel out with the 12 and leave me with a 3. And there's going to be a 1 left behind from the 4. And that's it. So now we'll go ahead and multiply these together. We'll still have m as our base. Negative times a negative means this will be a positive fraction. 1 times 3 means I'll have 3 on top. 1 times 7 means I'll have 7 on the bottom. And again, it's positive. Times n, again, negative times a negative means this answer will be positive. The 7's cancel out. The 6 cancels out with the 12, and it leaves me with the 2 up here. And everywhere else where all the numbers got canceled out, there's ones left behind. So we're going to have 1 times 2, which will be 2 on top, and then 1 times 1, which will be 1 on the bottom. And then to simplify this, we'll have m still. That'll still be to the 3/7 power. But then 2 over 1, 2 divided by 1 is just 2. And so we can actually simplify that fraction to a whole number. And so even though it doesn't really reduce because we already reduced it, if you can write the fraction as a whole number, it's preferable to write it as a whole number. So if you were to type it in like this to Math Excel, it's going to count that wrong because it's not the most efficient or optimal way of writing that number. You want to write it as just 2. Right. And this meets all the criteria. 1 of each variable, no negative exponents, and we simplified and reduced all the numbers that were involved. All right. And so that's how you simplify these exponential expressions when there's fractions involved. You just follow the same rules that we established earlier in the course. Let's take a look at these examples. I'm sorry, this problem looks like it's getting cut off a little bit here over on the left-hand side, so I'll rewrite it. It's the cube root, I'm pretty sure it's a cube root, of x to the 9th power. So we want to simplify this and use rational exponents to do so. So instead of trying to say, well, what raised to the 3rd power will give me x to the 9th power, which is one way you could try to answer this question, it's suggesting that we convert from radical form to exponential form, and it'll simplify that way. And so let's go ahead and try that out and see if they're right. So I'm going to rewrite this as an exponent. The base will be x. The power inside the radical will be the numerator, and the root of the radical will be the denominator of the fraction that becomes my exponent. And that's going way back to the beginning of the video with that formula that we were looking at. Right? That's how you rewrite a radical as an exponent. And then once I write it like this, we have 9. What essentially happens here is the power inside the radical gets divided by the root of the radical. And because those divide evenly, it simplifies very nicely. Right? 9 divided by 3 is going to give me 3. And so we get x to the 3rd power as our final result. So let's see if we can kind of exercise that shortcut here. So instead of taking the time to write it as a fraction, just remember this number gets divided by this number. Right? So the power inside the radical, negative 20, gets divided by the root, which is 4. 20 divided by 4 is going to be 5. And I guess more specifically, negative 20 divided by 4 will be negative 5. And like we were talking about in the previous problems, we can't leave our answer with a negative exponent, so that has to get flipped down to the denominator. So this will become 1 over x to the positive 5th power. And that's how that one's going to simplify. So again, the missing step here, I always feel bad leaving it out, but this is really the way most people handle this problem is take the power inside the radical, divide it by the root. But if you want to write it in exponential form, the power inside the radical becomes the numerator, the root becomes the denominator, you get negative 20 over 4, which gives you the same thing. It gives you x to the negative 5th power. All right, so that gives us an easy way of simplifying, easier than doing it this way, right? This way would be, it can be done that way, but it just takes a little bit more effort, I think. So I think this works a little bit easier. All right, we'll do the same thing here. Now what's going to happen, we haven't really talked about this yet, so I don't know if it's really probably not proper of me since we haven't officially introduced the rule, but this 4th root will just apply to each thing inside the radical. We're going to talk about that, I think, in the next video in 6.3. So we get the 4th root of 16, which is one you're supposed to memorize. The 4th root of 16 is 2. Right, it's not a square root of 16, right? There's a 4 here, so it's a 4th root. The 4th root of 16 is 2. And then what we're going to do with these is we're going to divide. We'll take the power inside the radical, which is 16, divided by 4. 16 divided by 4 is 4. And then 20 divided by 4 is 5. And that gives us our result. And the whole thing simplifies nicely in this way. Right? So you apply the 4th root to each factor inside the radical, and for the variable parts, you just take the power divided by the root, and that's how you get your new exponent. All right. I'm trying to think of another way that we could possibly do that. I guess, okay, this is probably what they wanted us to do. Right, so that's the shortcut I would use, and you get the answer pretty much immediately. They want us to use rational exponents, so what they want us to do is write this expression in parentheses. We'll have 16 c to the 16th power, d to the 20th power. And then we can write this radical, a fourth root, as a 1/4 power. So I mentioned that earlier in the video, right? A fourth root is a 1/4 power. And that 1/4 power is going to apply to everything that was inside the radical. So this is how you would convert it to exponential form. And then you'll take this exponent that's outside parentheses and distribute it into the parentheses, which is essentially what I just did over here with the fourth root. So I didn't have it in exponential form, but I used that fact over here. I distributed the radical to each thing inside of the radical, because you can do that here with the exponent. And so we'll get 16 to the 1/4 power. We'll get c to the 16th power raised to the 1/4 power. And we'll get d to the 20th power raised to the 1/4 power. And now that we've applied that 1/4 power to each of these, we can, at least for this case, convert it back to radical form. A 1/4 power is a fourth root of 16, which we know is 2. And then here we'll just multiply these together because we have one power raised to another power. So think of this as 16 over 1. You're going to get c to the 16 over 4 power here. And the same thing here. You'll get d to the 20 over 4 power. And then you just reduce those fractions in each case. 16 divided by 4 is 4. 20 divided by 4 is 5. And it's the same answer. And we did all the same math, just we did it a lot more efficiently over here by just keeping it in radical form. All right, but this is the way you're supposed to have done the problem in section 6.2. But feel free to use this shortcut. Apply the fourth root to each factor inside the radical, and whenever there is an exponent, just divide it by that root, and that's how you get your answer. All right, let's take a look at another example. Okay, so this is the most difficult problem. We only have 2 more examples here, so we're almost done. However, this is the most difficult problem, not only in section 6.2, I think this is a really difficult problem for the entire chapter. I don't know if it's the most difficult one, but it's one of the most difficult problems in chapter 6. So we cannot multiply these together as radicals. Not that we've learned about how to do that yet, but we will. I think it's in the next section. And you can only multiply radicals together if the roots are the same, which is not the case here, right? This is a fourth root. This is a fifth root. So they do not multiply together as radicals. Actually, this one's not as bad as I thought, I guess, because they're both x. If they were different from each other, then this problem would be a lot more difficult. So this is sort of the junior level to the problem that I'm thinking of. But what we're going to have to do to multiply these, this is going to be kind of tough because the 3 really does get in the way. All right, so sorry. Let's just see what happens. We'll see how difficult it is as we do the problem. In order to multiply these together, you'll have to write them as exponents because they do not multiply together as radicals. So we'll have to rewrite this. A fourth root, as we've said multiple times already, is a 1/4 power. A fifth root is a 1/5 power. So I need to use parentheses here because that fifth root applies to both the 3 and the x. So I need to put those in parentheses. And then a fifth root is a 1/5 power. So I'll rewrite that fifth root as a power of 1/5. All right. Now I can distribute this power of 1/5 into the parentheses here. And so they both get raised to the 1/5 power. So we'll have 3 to the 1/5 power, and we'll have x to the 1/5 power. Now the difficult thing here is they want us to write it as a single radical expression. So we have convert the expression into exponential form, but then once we simplify it, we have to be able to convert it back to radical form as just one radical, which means we can only have one fraction with one denominator to write it as a single radical. And because these denominators are different, we need to get them to be the same, right? And unfortunately, even though this is where I thought it was going to be easier for us because we can multiply these x's together, that's not a problem, but then the 3 will get left out of it. And so what we want to do is, let's not multiply the x's together. Let's get all of these fractions to have the same denominator. So find the common denominator, even though you're not adding or subtracting anything yet. The common denominator for 4 and 5 would be 20. So I'm going to make this denominator a 20 by multiplying 5 to the top and bottom. I'll make this denominator a 20 by multiplying a 4 to the top and bottom. And I'll make this denominator a 20 by the same method. And so we'll get x to the 5 over 20 power here, times 3 to the 4 over 20 power, times x to the 4 over 20 power. Now what we're going to do is something that we probably haven't really had to do before, which is the reverse of what we just did on one of these previous problems, what we just did here, right? So here, this power of 1/4 got distributed to each factor inside the parentheses, right? And then we were able to multiply these together to get this. But what we could do is we could, and what we're going to do in this particular example is the reverse. We're going to take a common exponent to each of our factors and undistribute it and go back to this, right? And so as long as you have the same exponent for all three of them, you can reverse that process and bring it outside parentheses. Like I said, we've never encountered a situation where we've wanted to do that in the past, but that's what we want to do here. So I'm going to rewrite each of these. I guess we'll go one more line down here. I'll rewrite this as 5 times 1 over 20. I don't know why I put 12. Oh no, I hit the wrong button again. All right, I'm going to have to erase it. So I've said this before, but the undo button is a left arrow and the previous page button is also a left arrow. They do look a little bit different, but when you're like glancing up, you're just hitting, I just want to undo, so I just hit the left arrow and I keep hitting the wrong one. Anyways, I'm going to rewrite this 5 over 20 as 5 times 1/20th, right? We're going to separate the numerator from the denominator, essentially. We'll do the same thing with this. We'll rewrite this as 4 times 1 over 20. And we'll do the same thing here. Rewrite this as 4 times 1 over 20. And then because we have that same exponent of 1 over 20 in all three of our factors, we can undistribute it. We can bring it outside parentheses. So I'm going to put parentheses here, and outside of that parentheses, I'll have that 1 over 20 power. And then what will be left inside the parentheses is x to the 5th power times 3 to the 4th power times x to the 4th power. And now I can write this as a single radical because a power of 1/20th is the same thing as a 20th root. And that's a single radical that we're writing there, which is exactly what the directions asked us to do. And so I'll have the 20th root of x to the 5th power, 3 to the 4th power, times x to the 4th power. And maybe you've already thought this, and I'm sorry I waited to the last minute to do it, but yeah, we want to simplify this. So 3 to the 4th power is actually just 81. And then now that the fractions are out of the way, that makes this much easier. So we could have done it earlier. We could have multiplied the x's together earlier, but it's actually easier just to wait until the fraction's out of the way, and then you can multiply these x's together. You'll add the exponents. So 5 plus 4 is going to give me 9. And then we're going to take the 20th root of that. And that's writing it as a single radical. So like I said, it's a pretty challenging problem. It's not clear from the outset, if you just look at this problem, how you would get there. So you have to kind of know this trick of write it as an exponent, get a common denominator, even if you're not going to add the fractions together, get a common denominator anyways, and then separate that denominator from the numerator so that you can put it outside parentheses. And when you put that denominator outside parentheses, it indicates a single radical at that point. And so you can write it as a single radical. All right, so that's how you do that problem. All right, last example here. We have 64 to the 1/3 power. Sorry, to the negative 1/3 power. So what I would do about this first is deal with that negative sign by flipping it down to the denominator. So this is going to become 1 over 64 to the positive 1/3 power. And then, as we mentioned before in this video, a 1/3 power is just a cube root. So this will just be the cube root of 64, but it'll be in the denominator, right? So cube root of 64 is going to be 4. So my final answer here will be 1/4. All right, so that concludes the video on section 6.2 on rational exponents.